Okay, can you hear me coming through the mic? Is it coming through all right? Is it loud enough?
It's kind of
Okay.
quiet, but I can hear you.
All right. Well, let's get started. You can see I'm still having fun with the equipment here. Tonight we want to discuss double integrals then. That's hard to see on the camera, is it?
The projector is blocking part of what you're writing.
Remember in Calculus 1, how was the integral defined, the definite integral? What did this mean when you wrote down this notation? Yeah, we defined the area under the curve to be that, but what is how was this defined? We thought of breaking some interval from A to B along the x-axis up into partitions from x0 to x1 to x2 to xn. So there were n subintervals, each of which delta x1, delta x2. Well, if you can see that on the camera, delta xn, I better draw bigger.
Can you zoom in?
And with the concept of getting the area under the curve, we said, well, we'll take any point we want in the first interval, x1 star, and go up to the height of the function there and make a rectangle of width delta x1. Maybe I should draw it up here, delta x1. Let's get rid of it here. And we'll do the same thing in the second interval at any intermediate point, maybe here, x2 star. We'll take the height. And at each interval, we'll take any point we want and get the height of the function, right? At times the width of the rectangle. And if we add up all those rectangle areas, we get this. We get the sum, k equals 1 to n. The height of the kth rectangle is f of xk star, right? Because we took the height at the starred coordinate within the interval, times the base was delta xk. That would give us the sum of n rectangles, right? If we break it up into this partition. Now, if we took the limit as the number of rectangles went to infinity, we called that the definite integral. Can you hear me all right online? Somebody speak.
You can't hear us.
Yeah, you can't hear us.
Yeah, I can't hear them again. Oh, great. Okay. Yeah, I see where it's blocking again. All right. I'll just write lower in that spot in the future. Shoot. Looks like I got part of it. Thank you. Boy, it'd be so easy to cheat on exams these days, wouldn't it? Boy, it's terrible. You have cell phone apps now that'll do all your algebra problems. You hold it over the problem and it solves it for you, which is real nice if you're an engineer, but if you're a student, you just can't have a cell phone on an exam anymore. Somebody hold it over the thing and get the answer to all their algebra problems. Plus, they can communicate with their neighbors and send pictures. They just can't have a cell phone at the exam anymore. All right, so the title up here was double integrals. I'll rewrite that. And I think they can see the
Dr. Stapleton, can you zoom in?
In Calculus 1, we make this definition that the definite integral from A to B means make any partition of the x interval from A to B into n subintervals, any whatsoever. Take the limit as the number of subintervals goes to infinity of the sum, height times base, of these rectangles. And then if f is negative, it's actually minus the height times the base. And as long as you do this such that the width of the widest rectangle in the partition goes to 0 as n goes to infinity, that's tacitly assumed in here, even though it's not in the notation. This gives you the same value regardless of how you pick the xk stars, which means if you pick the xk stars to get an overestimate on each interval, and took the sum, the limit is the overestimating rectangles went to infinity, you get a number. But if you took the smallest, the x star to get the smallest height on each interval and got inscribed rectangles, we call it, so we underestimated the height, the area in each interval, we'd get the same number. The limit as n goes to infinity is the same regardless of the partition for a continuous function f of x, right? That makes a suggestion that for continuous f of x, we define this to be the area under the curve also. So we'll define the definite integral this way, and we'll say if f of x is non-negative and continuous, then it's also the area under the curve y equals f of x, no matter how you choose the xk stars and no matter how you choose the partition. So that was calculus 1. Does that look familiar, I hope now? Okay, let's zoom it in then. Now, I left it zoomed out a little bit with the idea that yeah, thank you. Well, I need you here. That's what. Hopefully they can see it now. I was worried that I wouldn't be able to keep enough up on the board at a time if I didn't keep it zoomed out that far. Hopefully you can see it now. That's all review. Now, what are we going to do for calculus 3? Now, consider a function of more than one variable. Z equals, so this will be calculus 3 and 4. Calculus 4 will consider z equals f of xy, a continuous function of two variables, right? And maybe we want to find, since this is a surface, right? The idea is, in general, this one. You have some domain for a function of two variables as a plane region, right? We talked about this before. Here's your domain. And over that domain, you have coordinates here. And we call this the surface z equals f of xy. The set of points where you can take any point in the plane, x naught, y naught, and go up to the point here, then it's a height f of x naught, y naught. And then the three coordinate pairs here, you can think of this as x naught, y naught, 0 if you like. I just call it this because it's in the xy plane. But you plot the point x naught, y naught, f of x naught, y naught for each point in the domain, and then you get a surface over the domain. Suppose we want to find the volume under the surface. What shall we do in analogy to calculus 1? All right. So here's a surface z equals f of xy sitting over a plane region. Well, let's start with the easiest case. We started with just a simple interval here. Let's try a simple interval on each of the xy axes. I might have to move that camera over just a bit. Oh, can't do this. All right. There we go, sort of. I'm going to erase this picture from calculus 1 with the rectangles. I have a nice bunch of pictures for this actually that I can put up, but I don't know how to do it in this room yet. Maybe I can do it next time. We'll see if I can get it together. What we do now is suppose this domain D, let's call it, is a rectangle, the simplest case. Each axis has a closed interval. So x goes from A to B, just like in the calculus 1 picture. There's the x-axis coming out of the board. Here's the y-axis goes from C to D. And you got this rectangle. And now I've got a surface sitting up over the top here somewhere. Like that. C equals f of xy, and I'm thinking of estimating the volume under the surface. How could I do that? I could partition both the x and y axes up. I could partition this up into n subintervals of widths delta x1 down to delta xn, n subintervals. And then I could partition the y-axis into subintervals delta y1 down to delta yn. Right? So it's a lot like calculus 1, right? That's the ym. So m intervals here and n intervals here. Now, instead of adding up rectangles under the curve, I could think of adding rectangular boxes under the surface. In each little, this partitions the domain into little rectangles like this, right? Each of width delta xk and say delta xj and width delta yk. And over each one you construct a rectangular box. And you can think of adding up the volumes of the rectangular boxes because we know those, right? Just base times height times length. So it's very similar. So these are supposed to be rectangular boxes here. And we'll say that the double integral over the domain D here, need to label it D, of the function of two variables, dA is the notation. When we write that down, will mean a similar thing. This will be, well, let's see, what is the estimate we get? Here's the blown up picture. We have length delta xj, let's say, on the j subinterval in the x direction, and width delta yk, the kth subinterval in the y direction. And over the top, we've got a rectangular box, that's what all these things are, going up to some point on the surface. So here's the jk element, and here is a box. And its height, you take any point you want in the little rectangle down here instead of any point you want in the interval. Let's take some point, and we'll call it xj star, yk star. Any point you want. You go up to the surface is up here coming through here like this. You go up to the height of the surface, and that's the height of your box. And so the height of the box is f of some point in the little rectangle down here, f of xj star, yk star. All right. Now the volume of the case, we can say that we'd like to do this height f of xj star, yk star times delta A jk, where delta A is the area of the little rectangle on the bottom. Delta A jk must be width times length. It's delta xj delta yk. And then we sum k running from 1 to m times n, since there's mn little subregions, subrectangles here. Guess what happens to that if we take the limit as capital N goes to infinity? Let's put capital N up here, where capital N is the number of little subboxes, little m times little n. Subrectangles. As we partition n intervals in the x-axis, m intervals in the y-axis, there's m times n little rectangles down here in the domain. If we take this limit and f is continuous, it turns out, just like in calculus 1, it doesn't matter what point in each box we pick, xj star, yk star, no matter which point we pick, or how we partition it in the x and y directions, as long as the width of each partition goes to 0, and we pick a point in each rectangle, you get this sum is the same. You can prove it with a lot of finagling. Since it comes out to be the same, maybe that's what we want to call the volume under the surface, because after all, we can take xj star, yj star to get an inscribed rectangle. It's the lowest point on the surface over this rectangle, and get a sum, right? The limit of the sum. And the limit of the sum is the same as if we use circumscribed boxes, where you take the highest point and you get a bigger rectangle. So whether we inscribe or circumscribe or into something in between, we get the same number. This ought to be thought of as the volume under the surface, and therefore we define it to be the definite integral with the idea that if f is continuous and non-negative, we're also going to call it the volume. So this will be the definition of the double integral. Where just like in calculus 1, you secretly assumed that the width of the widest subinterval went to 0 as n went to infinity. Now, as capital N goes to infinity, you assume that the widest subinterval in both directions goes to 0. So for continuous functions, this gives the same result, and for some others too. Just like in calculus 1, you remember some other curves for which this gave the same number no matter how you partitioned it? There were other curves too. For instance, piecewise continuous curves, right? Where it was a finite number of pieces, each of which was continuous and didn't go to infinity on the interval. So if you had just a finite number of points at which there's a jump discontinuity, including possibly maybe it's just a hole, like that. Any curve that was piecewise continuous, this also had a fixed value no matter how you partitioned it. And there's some other curves too you can do. And there are pathological curves for which this doesn't work, but for nice curves that are at least piecewise continuous, for instance, the calculus 1 sum gave the same result. And similarly, for nice surfaces that are almost continuous, this will also work, but it at least works for continuous functions and some others. We'll make that definition with that in mind. All right, so any questions on that? That's the theory behind it. Then, let me move this over again, I guess. Now, for f of x continuous, on this part of the board I can write here at the top, I believe. For f of xy continuous on the domain, and also non-negative, we also define v equals the double integral with that definition, f of xy dA, the volume below the surface, z equals f of xy over d. So that's the definite integral definition when f of x is non-negative and continuous, so we can evaluate it, and we'll say that's the volume. That's all nice, but just like in calculus 1, it's pretty hard to actually calculate it, right? How many times did you actually calculate a definite integral from the definition here, right? Almost never. You might have done it with like ax plus b for the simple function. Then you say, it's too hard. We need theorems to be able to evaluate this, right? So just like that here, we need some theorems because this is too hard to evaluate. Theorems include these kind of things which are completely analogous to calculus 1. That's what's nice about today. So theorems include that the double integral of a constant times a function, I bet you can guess this one, what happens to the constant? Yeah, you can pull it out. It's the double integral without the constant multiplied by the constant on the outside. So the c comes out just like it did in calculus 1. Yeah, you do. You have to put it's like if you want a definite integral, you have to put from a to b in calculus 1. So you have to say over what region. So d is the region. Yeah. I think the book might use R for region instead of D for domain. You can use whatever letter you like. There are different calculus books use different letters. Here it's kind of nice to put R for rectangle too. So far we've just done rectangular region, right? Then F and G are yeah, thank you. F of x, y, dA integrated over d, and double integral g of x, y exists, meaning you get the same limit of the sum no matter how you partition that and pick the points. Then you can also calculate that the double integral of the sum or difference of the functions is the sum or difference of the integrals. There's the double integral of the sum. This is the sum of the double integrals. There's another theorem. All right, so that helps to get us started. Well, really, we need something much more powerful than that. Here's the biggie for rectangles. We'll get better theorems than this for more exotic regions. Now, the theorem of Fubini. Sounds like Houdini. It's a magic, right? Theorem of Fubini says that if f of x, y, and this is the one that allows you to actually calculate them without having to calculate that from the definition with terrible limit of the sum. Who can do that? It's too hard, right? If f of x, y is continuous on a domain D, which consists of, I'm going to introduce some new notation, AB Cartesian product CD. What does this mean? Let you guess. Yeah, it's not the cross product, it's the Cartesian product. Remember that Cartesian product, if I take two sets, A, B, C, and 1, 2, here's set A and here's set B. What's the Cartesian product of A with B? Remember? Set of all ordered pairs where the first one comes from A and the second one comes from B. So it'll be the set A1, A2, B1, oh, this is B1, B2, C1, C2. It's a set of all ordered pairs where the first element comes from the first set and the second one from the second. With that idea in mind, if we take AB Cartesian product with CD, this is the rectangle that we just wrote. That goes from A to B on the x-axis and C to D on the y-axis. The rectangle we've been using. Right? And similarly, we're going to use notation like this sometimes. This is extremely common in higher mathematics. You see this all the time. What then is R2 if I take R2? This means R the real numbers. Cartesian product with R the real numbers. What's that? Set of all ordered pairs of real numbers, right? That's the plane. That's the Cartesian plane. So let's call it the XY plane. You call the first element X and the second. It's all ordered pairs of a real number followed by a real number. So they're going to use this notation in the book. R2 to indicate Cartesian product R with itself, all ordered pairs x, y. It's just the plane, that's all it is. All right? Or they'll use AB, Cartesian product CD to refer to a rectangle. Suppose our domain is a rectangle, x going from A to B and y going from C to D, and f is continuous on that. Then the double integral exists over D as defined, the limit of that sum of all those rectangular boxes. And it's actually equal to the iterated integral, x going from A to B and y going from C to D, f of xy dx dy. That's the big theorem. This is what allows you to evaluate these integrals over a rectangle. And like I said, we'll get a better theorem for non-rectangles. Where we have to say what this means. This is really just calculus 1. So it says to do calculus 2 double or calculus 4 double integrals, we can use calculus 1 techniques. You don't usually put these on because it's extra notation, but this means you do this integral on the inside, and then you do this integral on the outside. It's an iterated integral. And in particular, the integral on the inside is a partial integral. Whatever one you put on the inside. What is a partial integral? Can you guess? It's a partial derivative. Yeah, you hold the other variable constant and just do the ordinary derivative you learned from calculus 1, right? So it's holding the other variable constant. Similarly, a partial integral holds the other variable constant and does the integration, the antiderivative. So holding the outside variable constant, treating it as though it's a constant. That's what it means. We'll do an example here in a minute. So you can do a calculus 1 integral, just pretending y is a constant like it's c, and integrating a function of c and x. Then you have an integral with respect to y. This becomes a function of just y. The x falls out because you integrate it. And then you have an ordinary integral from calculus 1 with respect to y to do after that. Then you say, well, wait a minute. Why does x have to go on the inside? Why can't it go on the outside? The answer is it can. You can do the integral from A to B on the outside, or the integral C to D on the inside, f of xy dy dx. Both of them work. Now let's get rid of the parentheses now. Nobody writes it that way. So let's do an example here. I'm going to have to move this over. Suppose I wanted to find the volume below the plane. Remember planes? X plus y equals, z equals x plus y in the first octant. How about that? What's the first thing you should do probably on that? Oh, I'm sorry, I don't want this. I'm not in the first octant. I want, let's say x plus y plus 1. Sorry, I should do this. Over the square, 0, 1 in the x direction, 0, 1 in the y direction. There we go. Sorry. Leaping ahead of myself. Draw a picture is a good idea. The idea is you're going from 0 to 1 along the x-axis, and then from 0 to 1 along the y-axis. and you're over this square. Now z equals x plus y plus 1 is a plane. When z equals 0, or when x and y is 0, you get z equals 1, so it's right here, 0, 0, 1. And you can plot some other points, like plot at the four corners. When x equals 1 and y equals 0, you get 1 plus 0 plus 1 is 2, so it goes to this point up here, 1, 0, 2. And if you put y equal 1 and x equals 0 over this point, then again you get 0, 1, 2. And if you put x equals 1 and y equals 1, z is 1 plus 1 plus 1 is 3. And so it's got this diamond on top. There's the top plane. Z equals x plus y plus 1. When we're asking what's the volume below that diamond and over the unit square in the xy plane? Well, since the function here is continuous, it's just a plane, right? In fact, any polynomial function, for instance, is a continuous function. And it's non-negative, we can say that the volume is the double integral of f of xy, where this is your f of xy, x plus y plus 1, the surface, dA. Right? That's by definition of the volume. It's the double integral of the surface. Now, how do we evaluate that? Fubini's theorem, right? This can be the integral, x going over its values on the, say, on the inside, 0 to 1. Y going over its values on the outside, 0 to 1. F of xy is x plus y plus 1 dx dy. So we can evaluate it now by calculus 1 techniques. This is Fubini's theorem. So magic, all of a sudden you can do it. Let me get rid of that. Not sure how far over I can go here. That should be it. So what do? We'll leave the integral on the outside and just concentrate on this integral on the inside. On this one, this is a partial integral holding y constant, right? Since we're integrating with respect to x. What's the integral of x treating y as a constant? It's just x squared over 2, right? What's the integral of y treating y as a constant? It's y times x, right? Think of integral of c as c times x. Integral of 1 is x. You just treat y as though it's c, and the integral of c is cx. Right? And let's evaluate it at 1 and 0 and take the difference. This is the fundamental theorem of calculus. I guess you can just see this. So use Fubini's theorem to write it as two calculus 1 integrals, where the inside one is a partial integral. Then you use the fundamental theorem of calculus that says to evaluate this definite integral, which is a terrible limit of a sum, you can use antiderivatives. You can write the antiderivative of that, plug in the endpoints, and take the difference. So it's Fubini's theorem together with fundamental theorem of calculus makes you able to do this without actually ever evaluating a limit of the sum, the definition. Right? So you plug this in. You plug in x equals 1, and you get 1/2 plus y plus 1. And then you plug in 0, and you get 0 plus 0 plus 0. And you take the difference, right? That's how you evaluate this thing. Now I just have this easy integral from 0 to 1 of calculus 1. Y plus 3/2 dy. That's easy to do, right? Integral of y, again, I'll apply the fundamental theorem of calculus and say to evaluate a definite integral, I can use the indefinite integral, y squared over 2 plus 3/2 y, evaluate the endpoints and take the difference. So let's see, it's 1/2 plus 3/2 when I plug in the top endpoint. 0 plus 0 when I plug in the bottom point. The volume under here is exactly 2. Yeah, 2 cubic units, yeah. Um, oh, I know, this looks funny to me. This is 113, I never marked the point. If you think about it, you can verify that result. How can you easily verify it? You could take the rectangular box that's halfway up here, right? If you took the rectangular box with the same base and halfway up here, it would have the same volume because the volume below the surface above it and the volume lost below it would cancel each other, right? Since it's just a plane, it goes up over the top the same amount as it goes below the bottom. Well, this one would be at 2 units high, and so it's a 1 by 1 by 2 box. You could verify, double check your answer that way. So we could have guessed that one. But this formula now works for much harder surfaces, right? You don't have to have just a plane over the top. All right, so that's the idea of the definite integral. Let's do one more here, because I want to illustrate one more thing. Suppose I want to evaluate, this time instead of writing volume, I'll just say, suppose I'm given a double integral over a domain D of e to the x plus y dA. Suppose that's my double integral. Maybe it's the volume below this surface, which is also non-negative. So this could be thought of as a volume. And I just said evaluate this. How would I evaluate that? Oh, I'm sorry, over the domain D. This time, let's make it a 1 by 2 box. It's 0 to 1 on the x-axis, but it's minus 1 to 1 on the y-axis. Fubini's theorem says I rewrite it, and I can write either integral on the outside. Let's put x on the outside this time. Integral from 0 to 1 on x, and minus 1 to 1 on y. The integrand, e to the x plus y, dy goes with the minus 1 to 1, and dx goes with the 0 to 1. The idea is the inside integral is this, so these have to be the y endpoints, and then you integrate x between these. This one has a little trick because the integrand can be written as e to the x times e to the y, a function of x times a function of y. You can rewrite it like this. You don't have to. You can do it just like the last example. But you can say this is the integral from 0 to 1 of e to the x times the integral from minus 1 to 1 of e to the y dy dx. Why can I say that? Yeah, in here, this is a partial integral treating x as a constant, so e to the x is treated as a constant. I can pull it outside the integral. I'll get the same result. Now, once I've done that, I recognize, wait a minute. When I integrate over y and plug in the endpoints, this becomes a constant, right? So I can pull that out of this integral, since it's a constant, and write integral from 0 to 1, e to the x dx, times the integral from minus 1 to 1, e to the y dy. Oops. And if you recognize this from the beginning, a function of x times a function of y, you can do this from the beginning, skip this intermediate step, and just come right down here. Write it as a product of two integrals, the integral of the function of x over the x endpoints times the integral of the function of y over the y endpoints. And so that's what people do quite commonly. That's why they do it. You pull the constant function of x out, and then you pull the constant integral out the other way. I need to move this over, don't I? Maybe I can put it over here. Now I can do each of these just by the ordinary fundamental theorem of calculus. Integral of e to the x is e to the x. I'm going to plug in 0 to 1. Integral of e to the y with respect to y is e to the y. I'm going to plug in minus 1 and 1. And so this is e minus 1. All right, I'm going to plug this one in. And this one is e minus 1 over e. Right? E to the 1 minus e to the minus 1. Multiplied. And so what do we get? We get e squared minus 1. There it is. There's the volume below this surface, e to the x plus y over this 1 by 2 rectangle. So try those for homework. Let me give these sections. This is out of 14.1, and these will be pretty easy this time. The ensuing sections will get harder again. The first section is always easy. 3, 11, 13, 29, and 31. If you struggle on those, the odd problems around them also have answers in the back. That's why I assign odd problems if you haven't been in my class before, so you can look them up in the back and see when you're right. If you have any trouble, though, just email me and I'll try and, or meet me on Zoom. And by the way, tomorrow I have to cancel my office and if X alone is a constant, you can pull it out. Yeah. All right, so maybe that's not hard enough, huh? That's it. Yeah, it just keeps getting harder is what happens now. I'm just trying to check the time. Now, what if it's a more complicated domain? There are nice theorems. There's one I was going to present, but I think maybe since we're losing so much time, I'll omit it and I'll just sort of say it. In fact, you can do this for more general curves. If you have what's called a simple closed curve, what is a closed curve? Circle's an example, yeah. Curve that ends where it begins. So closed means it ends where it begins. So this might be x of a, y of a in the xy plane. And it's the same point as x of b, y of b when you write a parametric curve, x of t, y of t going from a to b. And then maybe you traverse it this way. That's a closed curve. If it's a simple curve, that means it's not self-intersecting, so it doesn't make a figure 8 or something, right? This one is not self-intersecting. So if I have a simple closed curve like this, and furthermore, it's piecewise. Man, I guess I am writing the theorem, huh? Piecewise. I was just going to say it, but I can't resist. Piecewise smooth. What is piecewise smooth? Means you can break it up into a finite number of pieces, each of which is a smooth curve, and then put them end to end. So these are smooth curves. Remember what smooth is? It has a continuous derivative. So curves with a continuous derivative end to end. This is actually very important for engineers. They do line integrals in the plane, and they do piecewise smooth curves quite a lot. Is the most general thing they tend to work with. So smooth meaning it has a continuous derivative, so it doesn't have corners in it. Place end to end. So you actually can have corners in here where the piecewise smooth curve meets, but there's only a finite number of points where you have corners like that. Simple closed, piecewise smooth curve. C, in closing, anybody heard of the Jordan curve theorem? No? Nobody? I'm going to teach you a lot of new stuff in here just for fun. The Jordan curve theorem says if you have a simple closed curve like that in the plane, it determines a unique set of points inside and outside. Such a curve has an inside and outside. So with that notion in mind, when you have one of these curves, there's an inside and you can find its area, right? And that kind of thing. So we'll say encloses D. I mean, it's sort of intuitively obvious, but it's nice to know there's a theorem that says so. Jordan curve theorem. Has the double integral exist when f is continuous over the D, the enclosed domain? In other words, you get the same limit of the sum regardless of the partition and the points you choose, right? F continuous on D. So that's a nice theorem. That's a little too abstract for us. And but I just wanted you to see that you can do pretty general curves and this double integral exists. But some of those curves are so exotic. I mean, imagine this is not a piecewise smooth curve, but you ever seen fractals? Seen fractals before? Like here's the most famous fractal, the Koch star. You take an equilateral triangle and you take the middle third of each side like that, make it into a star. Then you take the middle third of each additional side, cut it out and put two line segments like that, and you keep doing this over and over iteratively forever. In the end, you get something with dimension more than, I mean, it's a one-dimensional curve, but in the limit, you get something more than one-dimensional. And this kind of curve does not apply to this. It's not piecewise smooth, right? It's got an infinite number of jangles in it here. And what you get is this odd-shaped star that in the limit is and goes to infinity. Look it up online, the Koch star. So we don't want those kind of rings, right? But we can do something a lot simpler. And one special case of this theorem is another theorem. Says this: suppose D is one of the following. One, let's put it this way, in fact, type 1. A type 1 region, and this is what you come up with in sciences and engineering all the time. This is exactly what they all use. Is this kind of a picture. The picture is better actually than describing it in words. X goes from a point A to a point B. And there's a bottom curve, y equals f1 of x. And a top curve, y equals f2 of x. I think they call it f and g in the book now that I think about it. Well, let's call it f1 of x and f2 of x. And then you have vertical lines of the sides, x equals a and x equals b. And if this is your domain for the function, right, this is what sits down in the xy plane, you've got a surface over that. That'll be called the type 1 region, where F1 and F2 are continuous. I might have to move that camera. Maybe it's okay. Yeah. Messed it up. All right. I'm not writing big enough, am I? Tell me when this is too small. Huh? The other kind is type 2. I'm looking at that screen and realizing it's probably too small. Type 2 is the same thing in the other direction. Let y go from C to D, and between a curve x equals g1 of y and another curve x equals g2 of y. X a function of y, and horizontal lines. Y equals C and y equals D, and we'll call this the domain D. If it's this type, with G1 and G2 continuous, that'll be a type 2 region. This encompasses most applications you're interested in, right? Now the nice theorem, this is the broader one, the one we really want. So this is the star for the night theorem. Says that if f of xy is continuous on plane region D, if D is type 1, this kind of thing. Curve on the, continuous curve on the bottom, continuous curve on the top, and straight lines on the sides. If D is type 1, then the double integral over D of f of xy dA can actually be evaluated as the integral from a to b of the integral from f1 of x to f2 of x. So you actually have variable endpoints depending on x. F of xy dy dx, where again this is an iterated integral treating the outside variable as constant. And now we just outmoded Fubini's theorem, because Fubini's theorem is the special case of this where you have a rectangle, right? This one here, if you let y go from C to D horizontal lines, then you get C and D, and it's precisely Fubini's theorem. So this is a generalization of Fubini's theorem to do a region of this type. All right? Furthermore, there's nothing special about the x direction. You can do the same thing in the y direction. If D is type 2, bounded by continuous curves on the left and right and horizontal lines on the top and bottom, then the double integral over D or R, whatever you want to call it, of f of xy, a continuous function, is the integral y going from C to D, and x going from the left function g1 of y to the right function g2 of y, f of xy dx dy. So it's in the other order, dx on the inside, dy on the outside, so this one. This is also a generalization of Fubini's theorem, right? If you make x go between a and b, then this becomes Fubini's theorem also. So now we can do more general integrals, and this is really as complicated as we're going to get for double integrals. Half the trick in using this now is just to be able to visualize this stuff so you can calculate the double integral. All right, you just got to check the time. You know, in their course reviews, what they ask in recent years, they got very smart. You know, the faculty were always worried about people coming in late for the lecture and, you know, losing student time. You know what they found is a better measure? Does the faculty member let you out on time? People get upset when you keep them over more than if you come in late for some reason. So anyway, I got to watch the time, right? It can be bad ratings. All right, so okay. I'll let you out early for that one, right? Anyway, no. So let's see. Now here's the example I started before. Now let's find the volume below the plane z equals x plus y, in octant 1. I changed it to +1 so I could do the rectangle. I'm going to just leave it x plus y as one. Yeah, thank you. In octant 1. I started to write that, and then I added the 1 so I could do the other again. So the first thing on these things to do is to draw the picture. What I want now, oh, it's not going to work. Is to think like this. What is z equal x plus y? Oh, I do want +1, don't I? Yeah, I'm sorry. Yeah, it was x plus y plus 1. Oh, golly. +1, yeah. You're right. And so it goes through the point. If I put an x and y equals 0, then I get this point. 0, 0, 1. It's obviously a plane, right? Because z equals ax plus by plus c. A linear function is always the plane. In fact, right, remember any equation you write is ax plus by plus cz equals d with a, b, and c not all 0 is a plane. So you know instantly this is a plane because you can write it in this form. Now what we often do to sketch planes is this. We'll find the intercept. People always make sure it intersects the axes in the right spot because you can look at it there. It's hard to tell in 3 dimensions where anything else is anyway. So if I put x and y equals 0 and cover these up, I got z equals 1. If I put x and z equals 0, then in order to make that equal to 0, well, I get y equals minus 1. That's not the one I want. It's 1 minus x minus y. Sorry about that. So it's got 0, 0, 1. Wrong problem. Sorry. Then if I put x and z equals 0, I get y equal 1. It goes through this point, 0, 1, 0. And if I put y and z equals 0, I get x has to be equal 1 to get 0 equals 1 minus x. So you just try plugging in 2 of the variables equal to 0 to find the intercepts, and you find these are the 3 intercepts for this extremely simple function. You'd be surprised how hard it is to do an integral of something harder. But here's how you often sketch planes is you'll find the intercepts, and then you can draw the triangle and say it's the plane that contains that triangle. So here's the plane, z equals 1 minus x minus y. That's in the first octant. Right, here's x, y, and z. I wonder what the volume is of that little thing with triangular faces, right? So it's got this side back here, and this side back here, and this side down here. Here's where the picture shines, right? Because now what we're going to say is we want the volume is the double integral over d, where d is the base here, right? It's the region over which the surface sits. It's that triangle of f of x, y, dA is the only formula we have to this point for computing volumes. And then you look at this triangle on the xy plane. You can look at the projection of the surface, if you will, down in the xy plane. And it's got this line like this, and then it's got the axes. And this is your domain D over which the triangle sits, right? The icosahedron, I guess you call it, with 4 triangular faces. And what do we know about these 2 points? These are the points with x equals 1 and y equals 0, and with x equals 0 and y equals 1 within the z equals 0 plane. So this is the point 1, 0, and this is the point 0, 1. Consequently, what's the equation of that line? There's different ways you can do it, right? One way is to use the 2-point formula, right? Y minus y0. I mean, you can do this for any 2 points. Y minus y0 equals x, y1 minus y0 over x1 minus x0 times x minus x0. That's the 2-point formula. So given 2 points, you can always do that. I say for this one, don't do anything so exotic. You've got a y-intercept 1, right? Use a y equals mx plus b. It's got y-intercept b equals 1. And what's the slope? You go down 1 and over 1, so the slope equals minus 1. The y-intercept is 1, so it's y equals minus 1x plus 1. That's the equation of that line. Use the slope-intercept form. Is really easy, right? And then this is my region D. All right, so according to the volume formula, or the theorem, the star theorem, we can say this is the integral, x going from its lowest value, 0, to its highest value, 1. Well, let's write it out. According to the thing, it's for a type 1 region. If we can actually treat this either as type 1 or type 2 according to that one. Let's do a type 1. and say then x goes from a to b, and y goes from f1 of x to f2 of x. This is the easier one to visualize because it's the orientation we're used to, of f of x, y is the surface, 1 minus x minus y. Dy dx. So that's by equation star. We can write it like that. Integrate the surface equation, bottom curve to top curve. Here's how you figure it out. It's the bottom curve to the top curve on the inside. It's type 1. I already erased it. It looks like this, right? A to b, y equals f1 of x, the bottom, to y equals f2 of x, the top. This formula is what you got, right? In the theorem. So you put in what's the bottom surface? Oh, it's this one, y equals 0. And what's the top surface? Oh, it's y equals 1 minus x, if I simplify it, right? Minus x plus 1 or 1 minus x. And so I can say this is the integral, x going from its midpoint to its maximum, 0 to 1. Y going from the bottom curve, y equals 0 as a function of x, to the top curve, y equals 1 minus x as a function of x. 1 minus x minus y dy dx. That'll give me the volume of this little region. I'm sorry, I said the wrong. It's tetrahedron. Anyway, tetrahedron is the 12-sided one. This is a tetrahedron, 4-sided triangular region. So I just have to be able to evaluate that. And once again, the inside integral is supposed to be a partial integral. So if I integrate 1 minus, I can't split up and pull part of it out because it's not a function of x times a function of y. I can't use that trick. I'll just integrate it directly. Treating x as a constant, the integral of 1 is, with respect to y, is y. Integral of minus x is like minus c, so it's minus c times y. Let's c is x. Minus x times y. And integral of y is the variable, is y squared over 2. And we're going to plug in the two endpoints, 0 and 1 minus x. Then I'll have to integrate with respect to x. So that's the partial integral, treating x as a constant. Now I'll plug in for y, this one, and take the difference. So this will be integral from 0 to 1 of, and everywhere you see y, you just put parentheses. Parentheses minus x times parentheses minus parentheses squared over 2. And put in 1 minus x. 1 minus x, 1 minus x, 1 minus x. So here's y minus x times y minus y squared over 2, where y is 1 minus x. That's plugging in the top endpoint. The good thing I picked a simple example. See how exotic this gets if you pick hard endpoints? The other endpoint we put in the bottom is just 0 minus 0 minus 0. Save myself half the work this way. dx. That's why this is a good example. So if I can integrate that, look, that's just a calculus 1 integral with respect to x, right? So I'll group the like terms. Let's see, this one is x squared minus 2x plus 1 if I FOIL it out. Subtract it and divide by 2 and subtract all of them. So let's see, I've got minus x squared here, and minus a half x squared here gives a half x squared. Then I've got minus x here, and minus a minus x here, right? 2x over 2 minus minus. So it's plus x here, minus x here, and minus x here makes minus x overall. So it's minus x plus x leaves minus x. Then the constants, we've got 1 minus 1 over 2, a half is 1 half. So you should wind up with that then, and then minus 0. So multiplying all that out and grouping like terms, we've got a half x squared. Wait a minute. Yeah, x squared minus a half x squared. A half x squared minus x plus a half. Now this one's then easier to do, right? This becomes 1/6 x cubed by the fundamental theorem of calculus minus a half x squared plus a half x. Plug in 0 and 1 and take the difference. Becomes 1/6 minus a half plus a half. These cancel. And you find out the volume is just 1/6 cubic unit. All right, so there's an interesting problem for tonight. And you can see these can do some pretty nice things in calculating volumes of three-dimensional objects. What we're going to find, actually, as we do more of this stuff, is we can derive a lot of those formulas you've seen before. Like, you've seen the volume of a sphere's formula. What's the volume of a sphere? 4/3 pi r cubed, right, for a sphere of radius r. We'll be able to derive some of these formulas you've seen using these multiple integral things in the future. I guess I'll leave the problems for this off. You might take a look, try a couple of these at the beginning of 14.2 if you want. I'll assign the problems next time. For now, just try the ones on Fubini's theorem where the region is rectangular. I think that's about 7:15, is it not? I mean, 8:45 in my last class. Yeah, so I've got about 1 or 2 more minutes if you want to ask any questions or add anything. Yeah. I've got one more I'm trying to grade. Monday, I think probably by the end of the weekend. I'll try and get them graded over the weekend. Oh no, okay. Well, see, everybody else had trouble too, so maybe I'll be nice. So that's what everybody always does, right? Whoever gets the lowest score, you take them out for pizza after class or something, and then bring the average down. You ever do that? All right. Is there another question? I'm sorry. Yeah, I think I put on the syllabus, didn't I put 87, 74, 61? So I'll curve it at least that far, but if it seems like some of the questions were too hard, then I'll curve it a little bit more, yeah. Yeah. I still have that. I haven't returned that yet. Okay. Yeah. Yeah, that was mostly just to practice that, so I've been lazy about getting that one back, yeah. All right, well, everybody go have a nice weekend. Try those problems, and you might try the first couple in 14 too, similar to this, and we'll do some more of these next time.